Astronauts to the moon.
Ignition sequence start. 3, 2, 1.
Houston, we have a problem.
Liftoff. We have a liftoff.
We copy you on the ground. You got a bunch of guys about to turn blue.
What you're seeing here is a mirage.
What's going on, everyone? It's Jaron from Jeranism, back with another live video for you today. It's Thursday. It means it's time for a presentation from Ranty Flat Earth, so it should be fun. Let me start off by saying thank you to all the patrons out there. You guys make this channel and everything I do possible, so I really do appreciate that. If you want to join them, you can easily do so at patreon.com/Jeranism, and while you're there, there's tons of other great content producers that you can support, so please do that as well. One of those is Ranty Flat Earth. Ranty, we're about to get started on your presentation, Refraction Effects Through a Homogeneous Atmosplane, with Ranty Flat Earth. So let me welcome him, Ranty. And by the way, I apologize that we are starting a little bit late, and we did start twice because, I don't know, something was going on with Restream.io sent the stream to the wrong place on YouTube. So I think I fixed it. We should be correct now. If not, somebody let me know. Somebody text me. But anyway, let's introduce Ranty. Ranty, how are you?
I'm good, thank you, Jaron. How are you?
Doing great. Happy to have you. You're a friend of the show. This is not your first time here, so hopefully people are excited to see another presentation. I am, and should be fun. But what's new with you?
Just, I suppose, concentrating on my show now. So, you know, essentially I am sort of socializing with the enemy, so to speak. So, you know, I do invite ballers to come on and do presentations and tell us all about their model and how it works and how they see things. And, you know, so essentially, you know, I get plenty of flat earthers on. I have plenty of chit-chat shows. But essentially, my main priority was to get these presentations done. And I think through encouraging them to come on and do their presentations, I've been able to formulate this new presentation, which I think is going to help a lot of people understand a lot of the observations that they see.
All right, cool. I'm definitely ready for it. And yeah, so people can look forward to my channel. I have a few other people lined up to do some presentations on coming Thursdays. I think Travis from Life is Short is going to do one. Iru is going to be giving his presentation soon, the one that he gave over in Spain. He's going to be doing that on my channel. We also have one from Rodrigo Ferrari Nunez is going to be talking about his Space Crack magazine. So there's all kinds of presentations coming up, so this should be fun. Let me start off by just showing people where they can subscribe to Ranty, obviously on YouTube. The link is in the description. All you got to do is scroll down and click that link, and boom, you're there. Ranty, do you also still have a Patreon?
I do, yeah. I did actually mention to people coming up before Christmas, though, that I was going to be taking a little step back for a few weeks, so I did. So I asked them to unsubscribe from my Patreon, which most of them did. And now that I'm back at it, you know, because I only had, I think, about 8 weeks off. Now that I'm back at it, it'd be nice if they came back.
All right, so if you're over there, yeah, definitely resubscribe or resupport or repatronize, whatever you got to call it, Ranty Flat Earth. And there is a little link up here at the top of his channel also that says help support this research, which will send you to his Patreon. So yeah, please do that. And then I also was reading a post from you the other day that said you're going to be missing from the Flat Earth debates a little bit. You want to talk about that?
Yeah, I just feel that the information that I've gathered from that up to now has reached its pinnacle. So there's nothing more for me to understand. I mean, essentially, it just seems like it's going over the same stuff now that we already know. There's nothing new coming out over there. So it seems like if you spend an hour there in the afternoon and then you've got the pre-show and the after show, that's 2 hours of your day that you're just recycling old stuff that you already know back to front. And to be fair, there's plenty of other videos that I can go watch and broaden my own knowledge base, so to speak, because I already know what they're going to say over there. I can predict each show as it goes along.
Right.
So it's just the way it is. So I'm moving beyond that for now, and concentrating on understanding a lot of other things because, like I say, I'm only getting a limited amount of information from that particular platform.
Cool. Yeah, always a good idea. I think sometimes even, I've mentioned recently that I needed to kind of step back and do more listening. So that's something I've been doing, and also want to be having these presentations. So if people are interested, if they want to give a presentation, kind of like Ranty does, or if you're interested in, maybe you have a channel with not too many viewers, not too many subscribers, and you want to get a post across or get a point across, a great place to do it is here on my channel. Come present. I would love to listen. We'll present it. And then if people like what you have to present, then they will follow over and subscribe to your channel. So it's kind of a win-win for everyone, which is why we're doing this. So welcome to the show. Welcome to Refraction Effects through a Homogeneous Atmosplane. Should be fun. And Ranty, if there's nothing else, then I guess we can go ahead and get rolling.
Yeah, sure. Yeah, well, I just wanted to also say that, there's no animosity there from my side anyway with the FED side. It's just that, we've outgrown each other, so to speak, and that's just the way it is. But, what can I say? I wish Nathan all the best. I wish the crew over there all the best. They do a great show every single day. People will still flock over there, I'm sure. It'll just be missing Ranty, so there we go.
All right, so if they want to find you, they can find you definitely on your channel. And do you have any regular shows that you do at a regular time you want to announce? Or?
Yeah, well, GMT, so Greenwich Mean Time. I do a show pretty much every single night, Monday to Friday, 10:30. Sometimes they can be just for an hour or two. Sometimes, like, for instance, last night, it stayed on for 5 hours, so I was up till pretty much 4 o'clock this morning. And, but that was just because the conversation was good. The people I had in, behaved themselves, and, it was able to go like that. But as for a regular show, no, it's like tomorrow night I've got, is it tomorrow night? No, so I'm recording one in the daytime, so I'll probably release it as a premiere. It's going to be a debate, so there's going to be a one-on-one debate that I'll be releasing. These are the kind of things I'm getting into. Also, presentations from Globers. I've got 2 Globers wanting to do a presentation. I've got 2 Flat Earthers ready to do presentations. I've got 3 debates in the planning, and also I've got my chit chat show. So it could be anything
Gotcha.
From one day to the next. It's just different. It's never going to be the same. It's always going to be something different.
All right, sounds good. All right, I'm putting your Skype on the screen so people can see whatever you're presenting, and let's get rolling.
Well, I thought I'd start with something. It's not on topic actually. It's nothing to do with this presentation, but it's more to do with how people would perceive what they're seeing in the 2 models. So, for instance, Slice Barcane, I know he's your best friend.
Oh yeah,
and
we go way back.
So Slice Barcane, you're getting some feedback.
No, that was just me probably talking over you. I said, yeah, we hang out on weekends. We go hiking.
Well, Slice Barcane saw this image that I took, and fortunately I had all the details, how exact location, height above actual seawater at the shoreline, everything that he needed to model it. So essentially there's an image on the right and an image on the left. And what he's done is he's kindly modeled out a flat plane versus what you would expect to see on a globe. Now, can you tell me, Jaron, off the top of your head, if you look at this image on the left and this image on the right, would you be able to tell which one was modelled on a flat plane and which one was modelled on a globe? Now, this is what you would expect to see through the viewfinder. So you're zooming in with your camera, you've got the focal length, this is reality, and this is a model and this is a model. But could you tell which one would be a globe and which one would be a flat?
I cannot. Wait, so you're talking about the middle is a real picture, and then you're saying on the left is something and on the right is something, and I'm supposed to tell you which one is which?
Yeah, the one on the left and the one on the right. One's modelled on a globe and one's modelled on a flat plane. But essentially, due to perspective and the distances involved between each one of these turbines, which is approximately about half a mile or a third of a mile, something like that. The effects of what you would actually see on both are pretty much the same. So the point here is that when globers see these turbines and they say, look at that, this curve there.
Right.
No. Your friend, Slice Barcane, your globe friend, modelled them out. And essentially you can basically tell no difference. I will reveal which is which, actually. So on the left-hand side is the flat plane, as you can see. All the bottoms are on the horizon, and on the right hand side you can see where the slope sloping away. So he has actually dropped them. The funny thing is that this image matches up more to the flat plane than it does to the globe.
Interesting. Yeah, I can see what you're showing there. So he basically modeled the one on the left to a flat Earth, the one on the right to a globe Earth. But to me, they look almost identical, other than seeing that they drop down.
Exactly. Exactly. So anytime you see these turbines in the future, these globers are going to say, "Oh, there's proof of the windmills splashing the water." Well, if this is a globe and this is a flat, well, you push the flat further away, what's going to happen? Eventually, the blades are going to start cresting the waves, the same as on a globe.
Right.
It's just something interesting. I just thought I would put that out there just to get things started.
Okay, and what was his? I don't know. What was his idea when he presented that? Just to show that they are identical, or was he trying to say that one was? Was he trying to say the one with the curve matches the picture?
Well, he did a live stream of it around about, I would say, about 18 months ago, something like that. And I guess he was trying to do a live stream to try and debunk this as being a flat, some kind of flat Earth proof. Because when we put the line through the center of these hubs, they're on a straight line. There's no perceived curve.
Right.
And I actually went to Barrow in Furness and filmed these from the side on. And you've also got a side on view, which when you put the line through them, they're absolutely flat. There's no deviation between them. So he decided to try and model this on a live stream. And what he did when he modelled it for flat and globe, essentially they look identical, but realistically, the flat plane, this angle from parallel, is more akin to this reality picture than this. This is too steep. This angle is too aggressive, whereas this one's not as aggressive and is more akin to reality. So it kind of backfired, I have to say.
Yeah, certainly seems so. All right.
Okay, so anyway, I thought I'd just talk about that. So I'm going to talk about, essentially, it's to do with light and refraction. Now, help me out here, Jaron.
Okay.
But would I be right in saying that the properties of light basically aren't very well understood?
I don't think they are at all, no.
Right, so some people claim it's a wave, some people claim it's a photon, some people say it's both. Some people say it's something completely different.
Right.
But all we know is that we see stuff.
Right, that's the facts of the matter.
How we see it, how it gets to us, it's all over the place. There's no scientific proof for it. I mean, you can look it up, is light a photon, and then for the most part, it acts like that. But they don't specifically say it is. It's a bit like gravity. Gravity acts like a force, behaves like a force. You can think of it as a force. But is it a force? Well, no, it's not actually a force. So trying to actually sort of like nail it down as to what light is and how it behaves, I think that's for me at least, I mean, if scientists can't figure it out, what chance do I have? You know,
I thought the
I'm
same
just a
too.
painter and decorator from Blackpool. You know,
It's funny when you listen to these guys, these physicists and stuff talk about it. They just, man, it's like endless debates back and forth. They don't have an idea, and they love to describe things like quantum mechanics as the best described theory in all of science, and then they follow that up right behind it by saying, but nobody truly understands it. It's like, great. So the best described theory in all of science, nobody understands. Fantastic.
Yeah, and from my perspective, I just go out and I film this stuff, and I take note of what I can actually see, and I spend a lot of time and effort going into this and trying to understand it. And one of the things that I absolutely hated was the word refraction, because I remember that from the first time I ever jumped onto any kind of platform talking to people about this, which was back when Asa Mahalski was doing his show. So that tells you how long ago that was.
Years.
And at the time, we were bringing out images of Blackpool Tower, and all we were hearing from the Globers was refraction. It got to the point where just the name refraction, it sent shivers down me. I hated the name, I mean, it's like, why would you even go near that? And so for the most part, I've tried to remove refraction from any of the presentations that I've done before. So I've talked about shoaling, which is physical blockage. I've talked about the inferior mirage and things like this. But actually getting into the realms of refraction, I didn't want to do that. And I'll tell you for why. It's because I didn't believe this idea that things can be loomed up.
Well, it's hard to find any evidence of it, yeah.
There is no evidence of, from what I can gather. I've got terabytes and terabytes of data. I've never been able to see any kind of looming happen. I've asked Globers for this kind of information. They've never been able to provide any of this. And I think the simple answer to it must be now that there is no looming, but there is refraction. It's just that there's truth and lies mixed together. Mm-hmm. And I think the globe earthers have got into this mindset that because they can see an image being distorted and they can see something happening with the image, that they also believe that light can be brought up from beyond the curve, the perceived curve.
Well, they have to believe that, right? Based on observations, they have no other choice because we're seeing too far. We see things beyond what we should see. The whole black swan argument, as far as where that horizon line is and why we're seeing so far beyond it. So they have to come up with something, and that's their get out of jail free word, which is refraction. Just allows them to say, oh, well, anything that you're seeing beyond what you should be seeing is simply looming or is being refracted upwards. So that's their kind of get out of jail free word.
So what I'm looking at here, Jaron,
are you showing anything or no?
Sorry?
Are you showing anything? I don't see your... I wonder why my Skype is frozen. Weird. Oh, there it is. Now we got it. Sorry.
Cool. Good stuff. Right.
Hopefully you were you showing anything before that?
I have no idea. Were we showing anything before that?
I don't know.
You'll have to...
If so, your screen was just frozen on my screen, so I couldn't see anything. But go ahead. Now we can see this.
Okay. Right. So, this is obviously the research into the inferior mirage. So what's going on here? Well, the fold on this top image here, which is basically, it's the same location, same observer height, same tide height, everything was the same. Even the conditions on the ocean, actually, they said the same sort of waves on the same day. On a different day, but the same kind of waves. It was almost identical. The only difference was this had an inferior mirage on this day, and this one you just saw shore to shore. Mm-hmm. The problem was that where this fold line was essentially going through here, mm-hmm. if you run it through the curve calculator, this here would be where they would say that the curvature of the Earth should have been. So anything beneath this part here, anything beneath this fold line, would have been lost to Earth curve in the globe mathematics.
Right.
So if we take this image on the good image that we can actually see all the stuff on, like this truck and on the shoreline here and this sand dune, all of that would have been lost to Earth curve if we lived on a globe. Mm-hmm. And when we look at this, and people will say, well, how can people believe that this is being loomed up and this is reality? This smudge at the top is reality if you believe the globe, and yet when you see this bottom image where it's really clear,
refraction.
And Yeah, refraction. It's being loomed up.
Right.
Yeah, right, okay, yeah. Well, to me, that's just utter nonsense. You know, it's just that we see very far without any atmospheric conditions, any refraction going on, and then when we've got some refraction going on, we get this. And I think what's happened is that they've reversed engineered optics. So
I think so too. Yeah.
we start with this. Let's say that this image here is the baseline. This is the optimal image, so to speak, with no refraction. Let's just give it a value of, say, 1, right? So this is just 1. This is 1. This is perfect conditions. You can just see for a very, very, very long way,
right.
Short to short, no issues. And then everything from then onwards is scaled back. But the problem is that this 1, where you don't get any refraction, probably only happens 2% of the time.
Right, it's rare.
This is probably, yeah, it's rare. This is only 2% of the time when there's no refraction going on. But this up here, this probably happens 70% of the time with this inferior mirage on. So what they've done is they've claimed this as the baseline rather than this is the baseline. So once you claim this is the baseline, then this image has to be being loomed up. And then anything worse than this, where you get more smudging going on, would be worse. It'd be, say, 10. If this is 1, that would be 10. So I think what they've done is they've reverse engineered all this optics and stuff, which I've talked about before. But it is in the refraction calculator. You can check this out, and you can see how they kind of model this. So that's my point here, is that when we see this is the exception to the rule, and in their model, this is all being loomed up. But to me, it's just a very clear image on a good day.
Right.
And this here is supposedly what you'd see 70% of the time.
Right. And so it makes sense that they have to scream refraction, they have to claim looming, because there's no other way out. I mean, otherwise you are seeing too far. In which case, as far as where the geometric horizon should be, how far we should see according to the maths, they can't admit that there's a problem there. So the correct answer for them is refraction, is looming.
Yeah. Exactly, but it's trying to understand what refraction is. Now, if you imagine or you understand that there's no looming going on, then the only thing you've got is what in their mathematics would be 76R. So their mathematics has a calculation for how much light is bending down, so to speak. So in their model, actually, 76R, it's upward refraction. So in their model, it goes up to start with, and then it comes down, right? But I'm going to get to this in a minute, that I've been able to talk to these globers who actually explain that on a flat plane, it would just go down. It would just head downwards. So there would be no looming up. It would just be downward trajectory of light. So this would be just headed downwards. So I'll get to this in a minute. This is the crux of the entire presentation, basically. So if we exclude looming, and then we just work on the idea that it's an Atmosplane, right, and we've just got a downward trajectory of light, then things will disappear from the bottom up. But it will be, obviously, things will get this inferior mirage as well at times. You'll sometimes get this inferior mirage that I've spoken about. But other times, I can show this in its stages, as it's actually happening, by this stretching effect that you get. Without an inferior mirage, so you can see for a long way, then you see a distant rock or something, or something in the distance, and it's being stretched at the bottom, and that to me is indicative of the lights being bent. It's being bent down. It's actually being stretched and bent down. I can perhaps get to that in a moment, but I want to show you this Walter Bislin's thing. Just bear with me.
No problem.
This one. So.
Thank you.
Advanced curve calculator. So this is Walter Bislin's advanced Earth curve calculator. Now, by all accounts, when they say it's advanced, you obviously think it's going to be best of the best, yeah. But they always say that there's refraction in the atmosphere. So this is on a globe model, and I'm just going to slide this red slider from left to right, and this is the target that we're trying to see here. This building over the horizon. So if we move the slider from left to right, you can see that this distant building is going up and down from behind the curve. So this is saying that we've got refraction going on. yeah?
Mm-hmm.
And this refraction is moving that building up and down. But what happens when we put it on a flat Earth? So we've moved it from globe now to a flat Earth perspective. And now we're going to apply the same logic. Now, they always say that refraction happens. It's there all the time. Well, let's apply some refraction to this. Well, what's happening? Well, nothing. The building isn't changing at all. It's not stretching. It's not warping. It's not going up. It's not going down. It's not losing anything of it. Why is that? If light bends down through the mediums and it goes from through to the denser medium at the bottom, it should be bending the light down. So things should be being missing from the bottom up. Yeah?
Should be.
Well, yeah. I mean, I've been able to get them to model it. so this is quite fun actually because. Well, let me have a look at Skunk Bay first. So I'm going to. You've obviously seen Skunk Bay before.
Mm-hmm. Of course.
Right. Okay. So if any people haven't seen Skunk Bay, this is the effects of a time lapse on over Skunk Bay. Looking over in this corner here where my cursor is, we've got a little lighthouse actually. So I'm just going to speed it up a little and just get it to the point where I need. Oh, here we go. So I've gone over it again, and what I'm going to do is I'm going to put a line through these trees at the top to see how much of a deviation happens on these lines on these trees at the top. And if you watch that, they barely move. There's a little bit of wiggling, but essentially it's not very much. That red line stays pretty consistent, except when I move the red line to the bottom, we see an awful lot of distortion. It's going up and down, it's bouncing around like nobody's business. So clearly there's a lot more happening at the lower part than there is at the higher part. This is the lighthouse. If we play this here, you can see the lighthouse. It will get stretched and warped and all kinds of things that happen into this lighthouse.
Do we know the distance of that lighthouse? I've never heard anybody talk about the lighthouse there. Do you know where this camera is and how far away it is, or have you never?
I do, yeah.
Oh, good. I've never really looked into it. I don't even know where Skunk Bay is, to be honest.
Okay, just bear with me. It should be the last stuff that I was looking at. So if I go to somewhere around here. Yeah, there we go. So there's where the observation takes place on Skunk Bay. Near Skunk Bay. It's one of these houses here. It's one of these few houses here. I can't be sure exactly which one because they don't provide that information on the website. Mm-hmm. But it's down there and it's across here, and this is the lighthouse that we're looking at over here. So let me scroll in. There you go. Can you see that little lighthouse there?
Yeah, I can see it.
Yep, there we go. So there's the lighthouse. I can get a measurement actually. I'll just put a new one in because I don't know which one that is, but I'll measure it for you. I was going to make a claim then and say I thought I remembered how many miles it is, but I would be wrong probably. Yeah, there we go. So it's about, 7.43 miles, 7.44 miles, something like that to the lighthouse. Okay. And they claim that the observer height is about 45 feet. And it's interesting in the distance too. I've got some mountain ranges over in the distance here. It's like that mountain range that's directly behind it. We should only see on a globe model about 45 meters of it. And I can show you that back on the video. Mm-hmm. That would be the one that's directly behind it. Where are we? Skunk Bay. So let's go over. Let's find it. So here, see this mountain range over in the distance here?
Yep.
And this one. See these mountain ranges over here? That you should only see 45 meters of this apparently. But you can see that where the lighthouse is way down here, it's clear that we're seeing an awful lot more of that than what there should be lost to anyway. But anyway, so my point is that here's the lighthouse. I'll stop it on the flash somewhere. Where is it? There we go. So there you go. You can see it flashing. So it's definitely the lighthouse that we're looking at. There's the mountains in the distance, etc. But this is real refraction, so the trees stay in the same height. They don't really bounce around too much. But everything low down, everything in this lower, let's say 15 meters or so, gets bounced around quite a lot. And I'm going to say that's just going through these gradients. Now, let's get off of that. I'm going to play a bit of Rumpus. Hope you don't mind. It was on my show, but
No, it's fine.
here we go.
Your presentation. Otherwise, I would.
So in this tank, we've got some sugar solution, and with the small concentrate at the bottom, then at the top. So we have a greater density here and a lower density there. And greater density means it refracts more, less density means it refracts less, and so therefore you get a curve which goes towards away from the normal, which means it becomes, so here's a little sample here of the light here, the laser here, it's coming in here, and it bends away from the normal following sort of Snell's law, although this is slightly playing with the rule, because in Snell's law only really applies between sharp boundaries, but the effect of the rule, we can apply the rule still in this case where we've got higher density, higher refractive index, lower refractive index, it bends, becomes more horizontal. And in fact, it becomes, and as it becomes more horizontal, it actually becomes dip. So you actually will get an arc over here. You have slightly lower density and high density, it bends towards the normal, so it bends more. So it will actually form an arc. So that's what light does in situations with varying density.
Yeah, so that's what things do with situations with varying density. I'll cut it off just too short for it to actually follow through with what he actually said then. But what he's done here is he's got this tank, and he's filled it with different things to make a density gradient, and he's angled the light up. So the light's angled up, the laser sets off, but the density gradient is forcing the light to change its direction, and it's pulling down. So he's explaining what happens. Obviously, he's angled it up to show it's sort of curving, because that's what they need on the globe model. They need this curve to go around the globe. So what they're showing here is that this density gradient can be shown that you can make an arch through these density gradients. Yeah. Mm-hmm. So that was his point of that presentation. Now,
if we lived in sugar water, yeah.
If we lived in sugar water, exactly. But we don't live in sugar water. But I think just for trying to understand that point, it was important. Now this clip is the kaleidoscope clip. Now this is how I sort of envisage what we're seeing, which is that there's no looming, but everything that we can see is being manipulated. What we can't see, we'll get to that, but things being loomed up beyond the curve just doesn't happen. But what we do see in reality a lot of times is this kind of effect where you can have this manipulation going on. I've got this woman here with lots of different heads around, a bit of looming here, all this kind of weird stuff going on. But you have to be seeing the person to actually get the rest of this from. Mm-hmm. You can't put her head out of the screen and then expect the camera to make this kind of picture. You have to have a visual of the person that you're looking at.
Right.
And the idea that things are being like loomed up like now, and then she's got a head up here somewhere, just doesn't happen. The cameras don't work like that. They have to see stuff first to interpret it, and then make all this adjustments with weird stuff going on. And this is how I'm kind of seeing the atmosphere. It's behaving a bit like this, but ultimately you do have to be able to see the thing that you're looking at first for it to be manipulated.
You got to have a line of sight at whatever you're looking at for it to multiply that.
Exactly. And we do see these kind of weird effects. Skunk Bay was just perfect for that. You saw all the dancing up and down. I mean, 1 minute it was up, 1 minute it was down. But the mean of that, let's say that was the head here, the rest of it's just distortion through the refraction process that's going on. But nothing's being loomed up from beyond anything else. If you look back at Skunk Bay footage or any footage, you can go through that time lapse and you will never see like a tree hidden behind another tree that looms up behind it. You've got to be able to see what you're looking at. The only thing that's changed in Skunk Bay is what's actually, let's go back to Skunk Bay, is what you can actually see. Everything that you can already see in this image is what's being manipulated, a bit like that kaleidoscope. But there's nothing in this image that was never there in the first place. There's nothing behind this house, for instance, over here, that's looming up. Or there's nothing over here that's suddenly looming up either. It's just what we can see.
Right.
Everything that we can see is being manipulated and warped. But everything that we can't see isn't being loomed up.
No.
Does that kind of make sense?
Yeah, absolutely. I mean, that's what we've always been saying about this particular observation and how it always works with water. And then, I'm excited to see Travis's presentation soon, because I don't know if you saw the video he put out today, but it's fantastic. Again, explaining how much information is, scrunched into that distant observation. And, how when you're looking at that water, we are only seeing the first, mile and a half real clearly. And then after that, you're trying to crunch, if you're looking at that lighthouse, 7 miles into basically what would be the equivalent of like a quarter inch on this screen.
Oh yeah, a few pixels. Yeah, it's like get that idea of perspective. When I went to and I climbed, where was it? I was at Nicky Nook. So I've got a video on my channel from Nicky Nook, and I did a presentation on Nathan's. And what we had was we was looking at Blackpool Tower, and beyond Blackpool Tower there was a stretch of water. Now I measured the angle and I measured the distance. Now I think in just probably, let's say 30 pixels or something like this, there was about 20 miles of water.
Right.
But right next to the camera, the bottom half of the camera, this part here, was say up to a mile away. So we had all this that was a mile away. Then we had Blackpool Tower in the distance, and then way over here up at the top, we had a few pixels of ocean, which was equivalent to a huge distance, 15, 20 miles. And it just goes to show that angular size change, how much information is trying to be squeezed into just a few pixels. It's almost impossible to distinguish which is which.
Now, how high up did you say that webcam is supposed to be?
45 feet, apparently.
Okay.
And
couldn't we do the same thing with
that.
the entire argument of the, where the horizon line would be? If I remember right, isn't 50 feet about 4 miles where the horizon is supposed to be?
Let me go to the curve calculator and have a look.
I could be way off on that. I'm just trying to remember.
Let's get the other one up. I prefer Metabunk for some reason. It's just... So we have a distance of 7.5 miles, and we have a viewer height of 45 feet. So, the horizon is beyond the target, so the horizon would be 8.87 miles away. Now, problem is, and it is kind of a problem, because we see water behind that, but mind you,
right.
We can't really tell.
Wait. At 50, if 50 feet, the horizon is supposed to be 8 miles?
45 feet. Let's
Okay,
have a look.
at 45.
So, yeah, viewer height 45 feet. The horizon, the refracted horizon would be 8.87 miles, and the geometric horizon would be 8.21.
Okay, yeah, you're right. I was wrong.
No worries. So, just is what it is. But going back to this presentation, so I've talked about that floaty land. Oh, and here's an image that the Rumpus brought up when my computer decides to work. So yeah, so here we go. So this is an image that him and his friend has been working on. They've got a whole presentation about this, how light rays work, how they're supposed to curve around around the shape of the Earth, etc. This red line is standard refraction, but it's still arcing. You see, it's still arcing, but because it's not arcing enough, it's actually raising up to the observer. So it's kind of like back to front. It's like this. This is upward refraction. Upward refraction, and it's causing things to loom up, or is it downward refraction? I can't remember now. My mind's a bit frazzled right now. But ultimately, they're all curving, and sometimes they're curving away. Like this. This is their model. The problem is that they have claimed that this sort of like archway going this way in this sort of trajectory is less frequent, because to get this downward refraction, you need things to go through the mediums, and it's warmer at the bottom, going cooler and cooler and cooler and cooler. Yeah, well, that's normal. That's reality. That's what normally happens. It's warmer at ground level, and it gets cooler the higher up it goes. Mm-hmm. So this bending down of the light rays happens 99% of the time. It's very rare you're going to get a cold surface just above the water and then it warm up. it's always going to be warmer at the bottom and then get cooler as it goes higher. So we should always be in this realm here where the lights are bending down. And this is important to get to my next point, how I'm actually seeing this working on a flat plane. And I've actually got them to essentially agree with me on this. So that's progress as far as I'm concerned. And we call it sinking. So have you ever heard of sinking, Jaron?
Mm-hmm.
Okay, so it's basically the opposite of refraction, or looming. It's basically the opposite of that. So let's do a couple of videos. So this first one will be, I think this is the rumper speaking again. So just listen to what he has.
Yeah. So here's the tank.
Yep.
And so in the tank, it's a uniform thing. So obviously this is not comparable.
Can I just confirm as well that the light, the light where it's emanating
It's coming from the bottom right. It's coming from the bottom.
It's angled up originally to then create the curve down.
Correct.
However, if you was to aim that light horizontal,
it would go down.
It
like
would
this.
go down. Yeah.
Because here, you see, that's what's happening here. You see, here the light's horizontal. This point here, the light is horizontal.
Yeah.
And then you can see it starts then to go down. I haven't got. There are other images to make it clear. It actually loops and forms an arc, but I've only in this image. I've only got it coming down a little bit at the end. But it will carry on going down and going to come steeper and form an arc.
Okay. So just to confirm, so if that light had been parallel, it would arc down.
Correct.
And eventually just hit the ground or whatever.
Correct.
Right. Okay.
Correct.
So it could be, in effect, modelled on a plane then.
Which is what this is. I mean, this is what this is. Obviously, the tank here is flat, and and it has a uniform gradient going upwards of less and less refractive index, and so the greater stuff on the bottom of the tank is greater refractive index.
I just want to clarify though that the only reason this is proof of this looming effect, as you've just mentioned, is because that the laser itself is already pointed up. If it had just been pointed parallel along the lines of the gradients, it would have still curved down.
Correct.
Right. Okay. That's perfect. That's just what I wanted to confirm. Okay. So you heard him. If the laser was angled parallel in this homogeneous tank, so this is a replica of what it would be like on a flat plane with these gradients going up. If the light was angled out straight ahead, it would just curve down. It would just curve down, and it would hit the floor. Essentially, it would just end up curving down through the gradients and hit the floor. The idea that they've got this curve to start with is because they've angled it up to bring it down. But if they just fired this laser straight ahead, it would go straight ahead, and then it would just fade downwards.
Correct.
Okay, so. Right, so that's the rumper. So then I went to Stingray. So this is Stingray. So I caught Stingray on a different day. Here we go.
Bending it down, translating it down in our view.
Okay, so can you model this on a flat plane and do the inverse of refraction on that?
I can, and are you ready for this? Because,
I am.
Because I could just take away the bend. So the bend is that.
Okay.
I've just now taken away the bend, and if I go get the lattice, give me a second. So this is near enough the geometric reality. We're looking dead straight down it now, in line with that object. You understand that, right?
Mm-hmm.
Now, if we automatically, if we take the principle that it's denser, the air is denser at the bottom and more dense at the top, then what we start to get is that.
Okay.
Dense at the bottom and lighter and less dense at the top. That's what we get with atmospheric refraction. In inverse refraction, where we would see things like inferior mirages that we do see in bands, sometimes would make it do that.
Right, can you carry on increasing that, please, just for the audience to see?
Oh yeah, it just goes down.
So can you go back to normal and then show what would happen if we have an inverse of refraction on a flat plane? Just do it.
Yeah. So the inverse of refraction is that it just goes down.
So it would disappear from the bottom up with just the inverse of refraction, yeah.
Yes.
And what weather conditions would be needed for the inverse of refraction? Can you explain? How warm would the water be, and how cool would the air be?
Rumpus will be best for this, but the only time we see an inverse of refraction, and that is actually light bending upwards, would be in extreme temperature differentials on a band very close to the water, where it would also present. Someone's really loud, by the way.
Well, why would it be extreme differentials to have an inverse, but it wouldn't take a lot of differential to make a normal refraction? Right. Okay. Sorry. Yeah. So I forgot I'd cut it off there. So yeah, essentially, what he's done here is he's modelled it on a flat plane. So I'll just scroll back through this. So what he's saying here is that on a flat plane, where if you have these gradients that the rumpus has just presented with this, the light bending down through the gradients just through the nature of light, you could be looking at a distant object on a flat plane, and all that would happen is that it would just sink. Mm-hmm. And the reason it would sink is because the light at the bottom, well, all the objects would be lowering due to this atmospheric gradient, but the bottom of it the light from the bottom would just never reach the observer.
Right.
It wouldn't get there. So you would get this sinking effect. So we can see this sinking effect. We can see evidence that there may be sinking going on. I'll get to that in a minute. But we can never see the looming part.
Right.
We never see the looming part, and I want to sort of like distinguish between the two. It's like the Globers need both. They can say light goes up and down. We can see it actually in Soundly's work. With the lights on his lake Tenses Bayou experiment.
Correct. When they go both up and down there, the lights on the right side.
Yeah, so they dance around, they go up and down, and but they just assume that this is what's going to be happening behind a curve. But hey, guess what? Soundly had visuals on those lights the whole time. You have to see these things to see the manipulation. You can't see things behind something else. There's never been a demonstration of like a house behind a hill that's been loomed up, or anything like that. It just doesn't happen. It's because it doesn't happen. The only thing that happens is that what the imagery that you can actually see is being affected, like the kaleidoscope. So,
and it seems to me the more you looked off into the distance, the more distance that you're looking at, that light would bend upward, due to the fact that the more dense part of the atmosphere would be what would start getting smaller and smaller and smaller. Obviously, the largest thing that you would be able to see in the distance is the part that has the least amount of atmosphere, or the least dense atmosphere, which would cause it to bend up. Yeah. But anyway.
Right. Okay. So I want to show you this video. You might have seen this video before. Maybe not. It's quite an old one. I'll take it off me. You don't need the volume on. But essentially, this guy, and I'm not interested about what his claim is. His claim is that he's placed this object behind on a bit of a slant, not much of a slant, on a driveway, and it's quite a warm day. And what he's doing here is he's viewing this right now. And what he's going to do is he's going to pour some cold water on this step to cool off the step. Mm-hmm. And when he cools off the step, you're going to see a change, right? So let me just take a print screen of that right now, because I haven't actually prepared this part. But I want to play the video, so let me speed it up. So here we go. He says it's seen over the curve. This is his claim. It's a Glober that did this. Mm-hmm. So there's where he claims the horizon is, or the edge of the step, or whatever it is that he's looking over. And what he's going to do now is he's going to splash some water on this. And I want you to see the change that happens. He's going to claim that there's looming going on in refraction right now. Right, so here's the water going on, and now we see a change. It settles down. I'm just going to pause it there. Mm-hmm. There we go. Can you see the change in the two?
Yep. Now you can see the whole clip.
Yep. Now you can see the whole clip. So you've probably seen this one before, Jaron?
No, I don't think I've seen that video.
Okay. So let me just pop this on here. And I just want to show you, because I'd worked this out before. I just didn't have time to do it today. So there's the original on the right before he pours the water on. Let's go to the next one where he's got where he's not moved the camera. The camera's stayed exactly the same. Everything's stayed the same. The only thing he's changed is the temperature between the step and what you're trying to observe. So let me just get it back up to there. So there we go. And straight away you can see a huge difference, right? So let me crop this.
And is this on a curved surface or this is on a flat surface?
Well, he claims that it's on a slight decline. That's what his claim is. I don't see it being that way. What I see here is this effect of the light, because this is a warmer area. This is a step here, this step, and this is still the step. Now this is nice and warm, so this light is trying to get to the camera that we're seeing it through. So we're trying to see this clip, right? And it's being distorted. This is definitely being distorted. Now, is it being distorted because it's been loomed up? He claims it's being loomed up. Well, let's just check that. Let's just put this line in. Let's put a big red line in, and let's just see if that's the case. Has the height of the clip changed its relative position? No. But when we look at this part of the object here, so we put a line through that black part of it there, can you see that no longer is in the right place? In fact, on this part here, where it was warmer, this black line has been pulled down. It's been stretched down, because that's where it should be in reality. When he's cooled the step off, and now you can see everything. Can you see where this band here that should be in this location, it isn't? It's lowered. It's been it's been pulled down. You can also see the same effect on the yellow band. So you can just sort of make out the yellow band on this. So I'm just putting it on the top there, but you can see that it's much lower than reality on this side. And also you see it with this whatever you call that, some kind of cheroot or something. But can you see that brown cheroot thing? Can you see how on the image with all the heat? So this is where all the heat is. This is the cooler. This is the warmer. And on the warmer, you can see that anything below sort of this area here, everything beneath that has been pulled down from reality. It's been stretched, and the image, what you're trying to see, it's been pulled down and stretched. It's very evident when you compare like by like, but you can clearly see that it's not been loomed up. You know, there's no looming going on here.
No,
right?
I mean, unless you're talking, I mean, and again, this could be done on a flat plane as well, and you would have the same results.
Indeed,
right.
Indeed. And that's the whole point.
Right.
The point is that this is demonstrating this stretching effect due to the heat. So what it's saying is that you can, because of this stretching that's going on, the stretching has overlapped the yellow. This yellow part here that should be visible. Let me change this to yellow. So there we go. So there's the yellow part on this side, and we want to see the yellow part on this side, but we can't see it. Why can't we see it? Well, we can't see it because it's being the stuff that's higher up is overlapping it. The image of that is superseding this yellow. This yellow can't be seen because the image is being stretched and pulled downwards. The light is being pulled down. So this light, this yellow that we should be able to see, has been pulled down beyond the step now. So you can't see it. It's been dragged down. Yeah? And that's the point, that we do see this manipulation just on this particular video. It's quite clear that there's two big differences, but there's no looming going on. But there's definitely movement from this portion down. Definitely movement. Right, okay, so how can we see that in reality? So let's have a look at some of these images. This one's from Miles Davis. Let's open with photos. So this is one of his more recent videos that he's put out, and I noticed an issue with this the first time I saw it. I was like, oh wow, look at that stretching going on. So here we have an observation from, this was from the top. It was quite high when he filmed this. So there's the reality picture. Here's an image from him up high, taking an image of the same one. I've managed to get an image that matches up. and here it is to the side. But what I want to show you is this one down here. So this is taken from, I'm just going to make some numbers up now because I can't remember. This is, let's say, 50 feet, and this lower one is from 6 feet, right? It's something like that. So this was taken from much higher, this was taken from much lower. But what I've done is, because he walked in the same direction towards this, is I've scaled it. I've scaled it to width, so that, you know, where this starts to curve down and where this starts to bend down, and this matches up. So it's all scaled properly to the width. The only thing that's going to change on it is its vertical stuff on it, and you can see that over here. Here we have a ledge. On the higher observation, and this ledge on the lower observation has been moved. It's been pulled down. So even though it's been scaled to width, to depth, you can see that this has been stretched and pulled down. The light has been manipulated, and now the ledge is down here, whereas it should be up there if this was all to scale. Clearly it's not to scale because there's something going on. It's been manipulated somehow due to the temperature gradients have been pulling the light down. Yeah? Absolutely, like a stretching downwards. Yeah, just like with the clip that I showed you on that video. It's exactly the same as that. Let's go to the next image. So this one was from when I tackled Simon Dan. He sent all his trolls over to my channel. He didn't like this video because he put a video out claiming that that this, which is the Ailsa Craig, and this from the lower down image, that this was missing. Now what his claim was that we were only seeing this top part of the mountain in this image here. That's what his claim was, right? And it's very evident and very clear for anybody with eyeballs to see that essentially we're seeing the same object, except from the lower image it's proportionally accurate left to right, but it's remarkably stretched downwards. I mean, you can see how much it's been stretched at the bottom part, how fat this boy is here. It's really fat and deep. But there's some points that you can pick out, like that little noggin there, you can pick out there. This archway here, you can clearly pick out there. This little ledge here, you can clearly see it there. And obviously this drop off on the right hand side, you can clearly see it down here. But you can see the stretching again, it's being stretched down. That's why it's so much larger in this direction. So you can definitely see this stretching going on distant images. You know, you can see it quite clearly. And I'm going to make some claims. I don't know whether they're going to pan out, but I'm going to make some claims that the light is being bent down. There's plenty of evidence to say that, and the Globers are all over this saying that light bends down. What's your feeling about this, Jeran?
Yeah, it's hard not to see that it looks like it's definitely stretching or being pulled downwards.
Right, let's who else have I got? So I've got that. Oh, here's another guy. Am I all right to play a bit from Modern Day Debates? Okay, here we go. Oh, better put that volume up, would help.
Let's see. We don't have too many more questions. Let's see. We do have one from Ranty Flat Earth. Thanks for your question. They said, can you ask McToon, so is there no refraction going on here? Does refraction through the mediums only happen on a globe? Upward refraction would cause sinking on a plane, right?
Yes, there is. You can pretty much count on there always being refraction. Yes, downward refraction will cause things to look higher. Upward refraction will cause things to look lower. And whether it's flat or a sphere, the effects of refraction are going to be similar. However, on a sphere, except for miraging, if there's not reflection, if it's just refraction, we would not see things gone. We would see things compressed or stretched, but not gone.
You bet. Thanks very much.
What?
Okay, so yeah.
Okay.
He's trying to say that. Do you want me to play that bit again?
No, I got what he's trying to say. I don't agree with it.
No, I don't agree with it either. What he's trying to do is he realizes that I've been sniffing around this and going after his friends with this. And I've put some hints out. And I think what he's trying to... This was the last guy that I asked this question to a couple of days ago. And I think that they're now getting aware that they need to try and distance themselves from this idea that the light would just hit the ocean and just never come back, right? Mm-hmm. But in their model, that's why we have a hidden value in their model. In their model, they would say... See, their argument is that on a flat plane, the light, that there's billions and billions of light beams coming from every single part of something that you're trying to see, and one of those rays will reach your eyeball at every time, right? And I said to them, well, how about on a globe then? Why doesn't that happen on a globe? Why do you have missing on a globe then? If all the light is going in all directions and it will always curve around and meet somebody's eyeball, it's doublespeak. It's doublespeak because they are trapped with this. They've hung their hat on refraction and the idea that light can bend down. And it's apparently well known that this is what happens with light. I'm showing that this can be proven in reality. I'm showing imagery that shows this effect in reality. And they're not liking this because essentially this idea that you can have this manipulation of light on a flat plane doesn't bode well. And it's why if you going back to this Walter Bislin's curve calculator, so let's just go back to this Walter Bislin's, that's why he doesn't include it in his. If you actually check on his advanced curve calculator and you put it on the FE, this building is shown to be there all times. Doesn't matter what refraction you put on it.
Of course.
You can, it's not sinking. There's no sinking going on. But let's go on the globe. You put a little, a little mound in front of that building, and now the refraction works. now the atmosphere is working. Yeah.
Yeah, how would that be possible? So it only is possible on a globe, he's saying.
Yeah, exactly. But, they don't want to address the fact that this would happen on a flat plane. But I've just played 3 clips there of people admitting that this would happen. And I've even got, in his own words, the Rumpus saying that, with his expertise in this subject, that light just would bend down and hit the floor if it was set off parallel by means of that tank example. That tank example. So let's move on. Yeah, don't freeze on me. So we've done that. So so today, for instance, I went down and did some videoing. So let me show you this. Right, okay, so here's the sea temperature today, Jaron. Here's the sea temperature. So it's 9.3 degrees, right? And apparently the current weather at the time was 8 degrees, right? Okay, so the temperature was lower than the sea, which was warmer. On the next slide, which isn't that one, this is the primary swell, and this is why I went today, is because at 3 p.m. we had a 0 to 1 foot swell, which is almost nothing. I mean, it's actually flat at 9 p.m. tonight, but it was 0 to 1 foot every 4 seconds, which isn't very much at all. And lastly, we'll go into the current weather. This is from AccuWeather. It says it's 9 degrees. And this was the visibility, apparently 16 kilometers, gusts around about 6 kilometers an hour, 2 or 3 miles an hour. So there was basically no issues with the weather. So with these excellent conditions, you would expect to see far, right?
Well, I used to think that way, but not since I've been to the Salton Sea and seen that there's a lot of other variables that come into play.
Well, here's the video that I took today. It's 4 minutes long. I hope you don't mind me playing that.
No, go ahead.
Okay.
I love me some Ranty.
Okay, so take number 3. And it is just after 3 p.m. now, and the reason I keep having to restart doing this video is essentially we have air traffic flying over like nobody's business. We've had helicopters, we've had planes. Hopefully now I may be able to talk through this and work this out with you. So, it's a little after 3 p.m. I'm down at the Mirror Bowl in Blackpool. The sea state is less than a 1 foot swell, less than. In fact, just a few hours time it's going to be 0, no swell whatsoever, and the wind right now is just 2 miles an hour. Now what that is doing is it's creating a very, very flat and almost motionless sea state. I can show you that if we zoom in just around about here. You can see there's just some ripples across the ocean, but barely any vertical movement whatsoever. Okay, so now that we have that sorted out, I want to address this issue of how the light is behaving in the distance. So normally from this location I can see the mountains over there, I can see Barrow in Furness, I can see Devonshire Dock Hall, I can see the lighthouse from this location. However, the temperature of the ocean right now is over 9 degrees and the air temperature is just 7 degrees. Now this gradient, so to speak, this gradient will encourage the light to bend down due to refraction. Now this doesn't matter whether it's on a flat plane or a globe, this is just the nature of how we view things. Now this can be perfectly demonstrated right now when I zoom into this location where I would normally be able to see these objects. You will see that I cannot see them, not only with my naked eye but also the camera. So we are picking up nothing. So with the sun being out, with the sea state being almost flat and motionless, you would expect, with clear blue skies essentially, to be able to see a very long way, but that isn't the case. And this is a perfect demonstration today, right now, of how the light is not able to reach the camera. It's not able to get to the lens of my camera or the lens of my eye. What's happening is that all that light, as it tries to head in this direction, is caught in that gradient that pulls the light downwards, so the light actually never gets to reach the camera. Now just think about that. The light is never getting to the camera. Now of course there may be other issues at play as well. I mean, there could be some particulates in the air that are causing a little bit of blockage, etc. However, beautiful day, beautiful conditions, you would still expect to see some, if not most of, the objects we're trying to view right now. So this is just, you know, me coming down today to do this for Jeren, to just show you how, under these conditions, even when you would think they would just be perfect for good visibility, we are not able to see things in the distance. I hope this has been of some help. I'll probably play this video on Jeren's later, and for now, I'll see you in the next one.
Now, did you say that the air was warmer than the water here in this case?
No, the air was cooler than the water was warmer.
Mm-hmm.
So the water was like 9.6 degrees. And we had, my car was showing 7 degrees, the AccuWeather was saying it was 8 degrees, and somewhere else said it was 9 degrees for their air temperature. So all of those three air temperatures would have been cooler than the ocean. The ocean would have been warmer, so that would have been...
So let me see if I understand the claim correctly. So you're basically claiming that the light from Barrow and Furness is being bent down and hitting the water, rather than the fact that the light can't fight through any particulates or any blockage or any atmospheric conditions. That's basically your reasoning for why you think we can't see across today?
Yeah.
Okay.
Gotcha. Well, not necessarily on this day. I mean, this was what I just saw today, and we had no visibility. I'm not claiming that that was the entire reason today. There's probably other things that were going on too. But it's got to the point where I've got so used to coming down and seeing an inferior mirage, or coming down and not seeing very far, that it is the case that this is more normal than it's used to be. That when you've got the gradients, warmer, well, colder at the top, and then it's just getting warmer, ever so warmer, right down to the ocean floor, then you just don't see anything. You just don't get to see very far at all.
Right.
I
think the
it's
incredible
playing
thing
out
is
with that idea of refraction.
Right. I just think the incredible thing is that, you can see on some days and some conditions you can't see on others. Of course, Globers would go out there on a day like this and claim curvature.
Yeah, I'd filmed in the rain one time, and I said, "Hey, because you'd only see about a mile," and I said, "Yeah, this is proof of curvature."
Well, nobody's claimed curvature better than, or they say proven curvature better than Ranty.
Oh, right, okay.
or maybe I'm up there with you. You and I are the only ones out there proving curvature, I guess. All right.
Okay, so I'm going to sort of like try and demonstrate what I'm trying to. Bear in mind, guys, I mean, I don't have the best of technology here, so I'm just working with paint. So you're going to have to bear with me. It is what it is. So this is essentially just a diagram that I made up, just showing this is the sea floor. This is like some water in the middle, and we have no atmosphere right now. So there's no atmosphere in this particular diagram. On the next one, I'm going to put some different colours of heating. So obviously we've got a bit warmer, and then it's slightly cooling off as it goes higher up to, you get quite high, a few hundred metres high, and it's a lot cooler up there than it is right down at the ocean floor. So here we have these temperature gradients, a bit like what the Rumpus had put in his diagram. And if he was firing the laser off from this side here, his idea would be that the laser would shoot up, and then it would arch, it would come to a level, and then it would start to pull down again, and it would curve down. And I asked him, I said, well, if it sets off on a parallel line, so let's just pretend this is a parallel line there. If it shoots it off in a parallel line, what would happen to the light ray? And we've had 3 Globers that have all agreed that the light would just start to bend down, right? So just naturally gravitate towards the warmer, denser region, which would be down here. That's how the light would propagate through these density gradients. So moving on, how would that work out if this human on the right over here was trying to observe this replica tower over on the other side of the lake? Well, let's have a look. Let's zoom in and let's see if we can figure this out. So from the observer's point of view, the light leaves, once it starts to hit these gradients. I could have just drawn the gradients right over and made it a little bit better, but I wanted to show you this through these gradients. So the light sets off in a straight line, and then as it starts to go through these gradients, it's being pulled down, and it reaches the observer. Same with this part here, and same with this part here. But what happens when we're talking about the really low stuff, the low gradients, the stuff that when it leaves the lower part of the tower, what happens then? Well, if it leaves the lower part of the tower and it hits this gradient here, it should just travel straight to the human eyeball, so the Globers would think. But no, because it's doing what the Globers say happens, that refraction is real and the light bends down through the gradients. It goes through to the denser medium. We've had the Rumpus saying that the light would just hit the water. We've had others claiming the same. It leaves from the bottom of the tower, it hits these gradients, and it never reaches the observer. So the observer never gets to see this. Same with the bottom part, just straight down, never gets to the observer. Let's move on. This is what you'd see without atmosphere. So looking across the water, you'd see that in the distance. This is with atmosphere. So already we've lost part of this tower because the light never reached the observer. It just fell into the water. But the whole image would be being pulled down through the gradients. So the top part would have started off up here, but it would have been lowered down, and eventually the lower part would just never reach the observer. Let's move on. So let's see what happens with perspective when we put some perspective in. So we're going to move these towers further away. Well, we're going to make them a bit smaller, because obviously to this guy over here, that tower from this distance is that big, but when you push it twice as far away, it's half as big. Mm-hmm. So what's going to happen? Can you imagine there, Jaren? So the light sets off, and it's moving through these gradients. The back tower is going through all these gradients due to perspective, and it never reaches the observer. Same with most of the second tower. and the first tower. And here we go. This is what you'd see, essentially. So with atmosphere, so this would be the middle tower. That would be the third tower. You might just see the top part of it, but the rest of it just would never, the light would never get there. It would just be being pulled down. Now, this is the Glober's own research. This is how they see light, light bending down through the gradients. On a homogeneous plane, this is what I've been asking, and on a homogeneous plane, George Netanyahu last night, had him on my channel, asked him this same question, another Glober. On a homogeneous plane, what would happen? Light bends down. Here we go. So this is obviously what you'd see. So there's these three images here looking through these gradients. This is what you'd end up resulting in seeing on a flat plane, not a globe. This is just on a flat plane using the trajectory of light through the mediums, and it actually just never get into the observer.
And why would it be different if the observer climbed a hill? So your observer on the right, he climbs a little bit of hill. He's going to see more of the bottom of those towers, correct?
Well, yeah, he'd be seeing more of the towers, so he'd be getting himself out of the gradient, so it would take longer for these gradients to have an effect. It's why when people like Jay Tolan Media go up high up in the atmosphere, high up on the planes and stuff, or the long distance photography, how high were they up when they did that? Was it 20,000 feet or something? So they were way high. I mean, they weren't anywhere close to this warm area, this atmosphere at the bottom. They weren't near any of that. They were 20,000 feet up, 30,000 feet up in a plane. Mm-hmm. Jay Tolan Media, he can see, 600-700 miles with his infrared. You've got the guy with the long distance photography. Is it over 300 miles that he's seeing from like 20,000 feet? Well, up there, the temperature's pretty much the same. The gradients, you don't have this huge gradient shift from the bottom, say, 20 meters or so. This bottom 20 meters where everything's happening. Eventually, things will all fall into that due to perspective. There's a very narrow band at the horizon where your eye meets the horizon, so to speak. And everything sort of falls into that. This 15, 20 meter gradient to your eyeball at, say, 10 miles away. Well, once you put a boat behind that, it also, you've only got a few pixels to play with. These things all fall into that band. It's just what happens. You lost for words.
No, I was just thinking, the great thing about these presentations is while I don't 100% agree with what's being said, but that's the way it always is, right? Whenever you hear something new and you're thinking about it, you're like, well, I'm not sure I agree with that, but it takes time. Sometimes it takes time, and that's why I like hearing this stuff, because I like to hear different opinions and I don't know, funnel them through and see what makes sense. For right now, I'm a little bit back and forth on this
skeptical
idea, but a little bit, but continue on for sure, because I want to hear more about it, and you've done a pretty good job of presenting your case.
No worries. Well, this is, we're trying to find reasons for why things do. Jose, for instance, has an image that, until I actually started thinking this way, until I started thinking about this sinking observation, Jose Gonzalez had an image of a water tower in the distance. And it's quite evident in that because it's coloured and it's etc., there had to have been sinking going on. Otherwise, that image would have been a glow proof. It was as simple as that. And it always flummoxed me. It was like one of the only observations that I've not been able to explain away. And yet, we can talk about things that we see, which is the inferior mirage, or we can talk about things that this compression that we can see. We can also see stretching and warping that are going on. We can see all these effects. But to actually go into the realms of this refraction sort of thing, it is going on the Glober's territory, but this is their argument. And basically, I'm just taking their argument and applying their same logic, their same trajectory of light through the mediums on a flat plane. That's all I'm doing. Is I'm
in that case, you're doing a great job explaining your point, because that's what I've seen out of this, basically.
Yeah, I'm just removing the ball. Take away the ball and apply their logic to observations. What would happen on a homogeneous plane? right? Where the gradients are all the same. Let's see what it says. Open with photo. So
Right.
in
that
this
case, there
region,
would be sinking, and in that case, you would lose things bottom up.
Yeah, exactly. It's exactly the point. Is that you can look up what refraction is, and you can look up the different signs of refraction. And so, you've got sinking. Sinking is a thing. It's actually down there. You can look it up. You've got inferior mirages and refraction and stuff like that. But they also include looming, right? They include looming, but there's no proof at all for any looming. There's no proof. It's never been demonstrated, never been shown. I've been looking for it. I actually spent an entire year trying to find loom using that post and the buildings behind to try and see if I could find any looming. Could never see it. Look in Skunk Bay, you never see it. If they remove that from their logic, this looming, if they remove that from their logic and remove the ball, they can only be left with the science, which is saying that the light would bend down through the mediums. This is what their science says. And in that case, you can apply it on a flat plane and things will disappear from the bottom up.
Yeah, I mean, my contention with a lot of that is if you do put it on a globe, then really you'd actually be looking through less dense and less dense, and you might get the bending of up. If you think about different layers of an atmosphere.
Yeah.
For instance, Rumpus's video, or when he put the now picture that you were somehow able to put that sugar water in a curved tank, which is just insane to think about. Anytime you start bringing the ball into play, it gets insane. And then you picture different layers that are all bending with the curvature of that tank, and then you shot the light through it. Certainly wouldn't curve around that tank. It would actually bend upwards.
Yeah, and the thing is, when I actually messaged you, I said this is going to be a contentious video. It's going to be a contentious claim, and I had no doubts about it that people are going to look at this and think, what is he talking about? Some people may get the logic behind it. I mean, it was like when I first started talking about the inferior mirage, nobody wanted to.
Well, the logic is there when you take what their explanations are, when you take their descriptions and you pull them onto a flat plane, then the same observations would happen. That part's not really contentious at all. Whether it's actually happening, whether that's the explanation for what we see or not, that's still up for debate.
Well, my argument is that people like Red Pill Philosophy, who's done an amazing video, shore-to-shore observation. I've got plenty of shore-to-shore observations. Here's another one. There's loads of people out there that are getting these really crisp, beautiful images. I mean, you can see this truck. I mean, I don't know if you can see it on here, but you can see the outline of the truck. You can almost see the wheels, but it's just behind the sand dune. I mean, if there was a guy in there having a cigarette, you could probably see him having a smoke. And this is 14 and a half miles away, right? And we're seeing this truck. I mean, you can see the archway of the truck wheel at the back there, right? This is good photography, right? Now, if the atmosphere is able to loom up things like this and present this as an image, wow, we are living in a special place, I tell you, because I don't even think an artist could draw it that good, right? But yeah, this is my contention, is that this is reality. Obviously, this is just on a day without refraction, but this is what the Globers will say. This to them, this is the Globers' reality.
So my question would be on the top image there. Would you be saying that the lines of sight or the light from lower than that lighthouse or whatever are bending down, and that's why you can't see the rest of that hill that day?
It would appear so, yeah. I mean, if the light is bending down, because don't forget, the light rays, as the higher up, they're supposed to be traveling faster, right? So the lower down, they struggle to go through the denser medium, so they slow down ever so slightly. But that overlapping, I was trying to sort of think of something that would sort of like show you, but I didn't want to put this out there because if I did, I would be called it for the rest of my life. And that would be, have you ever heard of a prawn ring? Have you ever seen a prawn ring that you can buy? Or a king prawn ring?
Prawn ring?
Yeah, have you ever seen a king prawn ring?
No, I don't even know what you're talking about.
Well,
maybe it's a UK thing.
Yeah, it probably is, but it's like they have these prawns in a circle. They put like 50 prawns and they put them in a big circle, and they have the back parts of the prawn are headed sort of like dip towards the center. So you get this kind of like repeating sort of like swirl going around.
Gotcha.
The top part is always bending down towards the the middle. So it's like this top part here is in their model, well, in their science, is moving quicker through the medium than the part beneath it.
Mm-hmm.
So when it gets to the really thick stuff at the bottom, you get in this inferior mirage, which is causing the blockage, and it's because the light from the top is traveling faster than the light in the bottom, and that light at the bottom can't escape because there's light superseding it that's going faster.
Okay.
So, I mean, this is, to me, I mean, that's their reality. That's their reality here. That's where their curvature calcs say this would be where that fold line is.
Right.
But to me, this is reality, where you see a guy that essentially could be having a cigarette in his van, and you can just see it, and to try and then if you reverse engineer backwards on this, and you take their mathematics, not their 7/6R, take away the R part, and the 7/6 and all that stuff, but inside of all that, there is some mathematics.
And you're sure that white thing is a truck? I mean, you have video of it moving. It's not a house. It's not a building. It's not.
It's a truck.
Yeah, I guess it looks like it. Okay.
Yeah, you can see the flat back at the part there, flat back at the back there. That's where it falls off. There's the wheel hub.
Yeah, it looks like it.
Yeah, it's definitely a truck. But yeah, so inside of that, they have the mathematics to explain this illusion. That's how they came up with the curve. When they had this distance here.
Right.
But they were able to formulate a mathematical concept around a globe and give a mathematical, sort of like formula to work this stuff out. Well, all we need to do is reverse engineer that formula, and start off with something on a flat plane with this type of imagery as being the baseline. This is the baseline, perfectly shore-to-shore, beautiful imagery, right? Okay, that's the baseline. And then let's re-engineer that backwards and say, well, okay, so on certain days, you're going to have a little temperature gradient difference. Not much, just a small amount, and I've seen this before, the inferior mirage isn't as high up on this. The inferior mirage, actually, the curve, this pullback on it, starts around about here where my cursor is, so it's much lower. So what it's showing is that this will bounce up and down. This amount will bounce up and down. And so you start from the good, and then you reverse engineer it back. And that's what I'm leaning towards. As I say, I mean, you might not agree, but let's open with this photos here, this one. So you've seen this image before, Jaren?
Yeah, absolutely.
So yeah, two different boats, two different observer heights. Two different heights on the inferior mirage. Now, the thing is that if you actually work this out, and they're on two different levels, obviously, so where the inferior mirage is, it cannot be where the curvature of the Earth starts, because if the curvature of the Earth was here on this one, well,
totally.
How come that one's got one too? You can't have two curvatures. But what you can have is you can have this downward trajectory of the light, this refraction bending things down. And what's interesting is, okay, this image might not be the best one to show this as per the gradient, but if you actually work this out, because this boat was only a couple of miles in front of this boat, and it was much smaller, and this is a giant boat in the background, about 100 foot tall. So the gradient of this inferior mirage would be, I mean, it would literally be shooting up just like you'd expect the curve calcs. Let's see if I've got that. Yeah, so here, so forget this image for now, I'll get back to that, but let's apply this on the boat. Let's say this would be the archway of that you would get, because this would be the missing, the boat in the foreground that's only, say, 20 feet tall, the boat just a couple of miles behind it that's 100 foot tall, and most of that's missing to the inferior mirage, but the steepness of that gradient would be an arch similar to the 8 inches per mile squared, because they have to square it. They have to give this function of square. And I think that's what's happening. I mean, I could be wrong, but here's another image. I mean, let's go. This is another image of the two. Hang on. I wanted to show this actually. It's frozen on me. One sec. So yeah, so here's another image from the same location, right? So here we have a boat in this particular image, and we have this massive inferior mirage going on. So the orange line going through the inferior mirage on the boat, and the red line going through the inferior mirage on the mountain behind it. Now again, they're in two different heights. You know, there's two different heights on these. And this mountain in the distance, it's clearing these buildings of Barrow. So the buildings of Barrow are like 160 feet above sea level, and this boat is only 20 foot tall. So it's half the distance, this boat away to that. So you would expect, so the gradient would be a huge swing up. Here's what it looks like without the inferior mirage. All these buildings are hidden. All of these buildings are hidden.
And that's same height, right?
Same height, same observer position, everything. Nothing's changed. It's just a different day with the inferior mirage.
Right.
On this particular day, everything was wiped out. Right? You couldn't see anything.
Right. And that's the difference when we go to the Salton Sea, when you're able to see mirror flashes, when you're able to see laser flashes. You know, if somebody's at the beach there in front of those buildings and they're trying to send a laser across in the bottom atmospheric conditions, it doesn't reach.
Yeah.
Mm-hmm. And then if you're trying to do mirror flashes from that bottom, I see what you're saying. You know, it's the same thing. Is the weather causing it to bend down, hit the surface, and never reach your eye, and this way you never see it. And all you're actually seeing is basically a reflection of what's above it.
Yeah. Well, that's what I think is causing this inferior mirage reflection. So like this post in the foreground here, this post is 4 miles away. Well, we're still seeing some of this post at 4 miles away.
Right.
But you're 18 miles away. All of these buildings are missing. Now,
and it's even the water beyond that post is not reaching your eye.
No, nothing. You know, neither the water, neither the building. In fact, you can see where this post in the foreground at 4 miles away. All around it is these buildings. All around it is the buildings.
Mm-hmm.
But look here. Look here. All the buildings. You can see the post, but now you can't see the buildings.
Right.
So something is causing a blockage between this post and those buildings.
Absolutely.
There's a blockage happening. And as I say, I mean, this arc would be a steep curve. It would be a curve because there's 160 feet or so of building there, and this post here is only about 20 feet tall at 4 miles away. This is at 18 miles away. So if it was on a level trajectory, a level straight line, you would see some of these buildings, but you don't. So it has to be being arched too, which makes me think that of this great, you know, with the light being pulled down. The light would be being pulled down. It would never reach the observer, but it would give this effect of this inferior mirage.
Now, what would you say if a glober came and said, okay, well, when you can see it, that light is being pulled up?
I would say I have never, ever seen proof of that. In fact, I have been to this location so many times, and this post has been my savior in a way, because I've had this building behind it.
Well, and even if the light was being pulled up, I mean, you couldn't maintain the shape of that building all the way across anyway. We see what happens when it's being pulled down. Pulled down causes it to basically disappear. When it's being pulled up, I think that's when you get those, Fata Morgana, if you want to call it that, the upside down reflection.
Yeah.
Above, yeah.
And this post, in relation to this building, always stays in the same position. It never changes.
Right.
Never, ever changes. It's always there, right there. That's why I was looking for looming, because if there was glooming going on,
then you would
at times I would expect to see this building.
Rather than when you see it, it's there. When you don't see it, it's the light's not reaching you.
Yeah. So definitely we've got blockage going on here, right? So we've got a boat that's partially hidden. Then we got this is only 4 miles away.
Right.
But look at how the inferior mirage has already wiped out most of this water. You know, it's like, and all the buildings are gone.
Even the bottom part of that post can't be seen.
Yep, nothing can be seen. Can't just be anything to. It could be nothing to do with Earth curve, that's for sure.
No.
So there's something else going on. So it's possible that, I mean, I've been talking about atmospheric conditions. It could be like this mirrored water layer. It could be this evaporation of the water on the ocean.
That's why I was asking
all
you.
These effects.
That's why I was asking you if the temperature above the water was, a little bit warmer, or if it was colder.
Oh, right. Okay. Yeah. Well, it's always going to be slightly warmer, isn't it? Because the evaporation is happening right above the water.
I would think so. Yeah, and then that's going to cause particulates to rise up. Yeah.
Yeah, and for the longest time, I thought that was the reality. It still might well be. This is me just putting something out there for other people to chew on and consider, because at the moment I've had 3 or 4 globers all admitting that if you set light off on a flat plane and through a homogeneous gradient, the light would bend down. So if we're looking at across in a homogeneous plane here with the atmosphere and the gradients, with warmer air at the bottom and then colder at the top, even with their science, the light would say that the light would just bend straight down and just hit the water, would never get to the observer.
Mm-hmm.
And that is essentially what we're seeing. You don't need a globe for that. You don't need to put a globe in that.
It would be identical on either one. If they're saying it works on the globe, which, I guess the science or the mainstream would say that's the case, then certainly if you put that on a flat plane, you'd have the same effects, and you'd lose things bottom up the same way.
Yeah, exactly. You would definitely lose things bottom up exactly the same way. And it's been modelled, and they weren't going to model it on the flat plane.
Now,
they tried everything to get out of that.
Is there times where
to ignore it.
Is there times where you go look at this exact observation and you get those buildings covered by what looks like water? Or never?
The bottom part here, like an inferior mirage.
Right.
Yeah, loads of times.
But when that happens, I'm saying, does it look like water, or can you tell it's the same thing that's happening on the bottom image?
It's not as prominent or as pronounced as this, by any means. But it's a definite inferior mirage. It's more like this on this boat on the right, where you definitely see the mirror reflection of it. So there's 2 ways we can move forward with this kind of research. Is that if they want to claim refraction happens on a globe, they have to demonstrate looming, right? Mm-hmm. And they can't demonstrate that. It's never been proven. I've never seen anything of that ever at all. But I can apply their same logic on a flat plane and get things to disappear from the bottom up just by using refraction, right? Just using their logic.
Yeah, absolutely. And then the guy who showed the clip picture with putting the water on the cement there, again, that's not a curved ground. Is that what he's saying? Is basically if we put that on some sort of a curved asphalt or something, and we poured water, that it would bring something up from behind the curve? Is that kind of what he's getting at?
You mean his video? Right.
Yeah.
Let me find his video and play it again. Actually, so here we go. So this guy, let me mute that. So this guy has put this clip behind what is supposedly a little bit of a ramp, like on a driveway, but the driveway is ever so slightly angling away from the camera, and this is what we're seeing on a hot day. So the whole asphalt floor or concrete floor, whatever it is nice and suitably warm. And then what he's going to do is he's going to throw some water over it now, and he's going to cool that area down. And suddenly it reveals the reality of what we're trying to see. This clip, not all of the clip, bearing in mind, but much more of it. I think that there's still some of that clip behind that, because he's not been able to bring it back. But one thing we did when we analysed it is that this never moved, that never loomed up, but this was definitely stretched. That wasn't visible.
Right.
And I'm going to say that if that's...
But the same thing would be true on a flat plane, is what I'm saying, right? You're looking across the water, and on this particular day when it's warm, when there's warm air above the water, then we're losing the bottom of distant buildings.
Exactly. Well, that's the whole point. That's right. Exactly the point. So when I was looking at those, when I was putting those towers in, and I was looking across a lake, with my paint.net drawings, we were missing some of the tower. It was lost. that yellow band you can't see, they would claim that that's just hidden to Earth curve. But on a different day and in different conditions, when there's no refraction going on, suddenly, the atmosphere, a bit like nighttime. At nighttime, when you go out and observe at nighttime, things have settled down. You can generally see much further. And here's another example of that.
So if you went out during the day or even at night, and you saw those little lights there, you may be able to see the lights at night, and then you wouldn't be able to see them during the day.
Yeah.
If there was little lights down by the yellow line.
Yeah. And there's been plenty of observations. I've been to Barrow and Furness. I've seen shore to shore over 18 miles at night time. I've seen to the mirror ball, the big one on Blackpool, all the illuminations up along the promenade. All should have been lost to Earth curve. Not a prayer.
It's the same thing.
Things just settle down at night.
Yeah, no, we've seen laser flashes from 28 miles at the Salton Sea. We've seen the plumes from the geothermal plant, and those are only visible, or were clearly visible, at least at night. And then when the day comes, all of a sudden you get that same kind of effect as you have before we can see the entire clip here.
Yeah. And it's like Wide Awake's just said, an object must be within your line of sight in order for these optical special effects to occur. Couldn't agree more. I genuinely couldn't agree more.
Absolutely.
It's what I was talking about, this kaleidoscope effect.
Line of sight is everything.
Yeah. These things only all these effects, all these inferior mirages, this stretching, this warping, but you have to actually see the object for this to actually occur. Right. We can demonstrate that those effects because we know we can see these things, but they can never demonstrate looming. That's the whole crux of this. They need to incorporate looming into their refraction index. They have to prove it, but they can't. Whereas we just take their same science and their same mathematics, we apply that on a flat plane to something that we can actually see. We can get these effects going off at the same time, but ultimately we can start off from a position of an excellent observation shore to shore, and then you just work back from that with different areas of refraction, different amounts of refraction, and suddenly things start bouncing up and down like Skunk Bay, but nothing is ever loomed up from behind anything else.
No, I would agree with you. A couple super chats. We got thank you from the Shape of My World 13. Thank you for that. Miguel Beaumont, he says it's flat. Thank you very much for that. Delano Gaston said, I vote to have the 2020 Flat Earth Conference in Atlanta this year. All right, I'm not the person to talk to about that. I don't know actually who is, but Jeff Gale, thank you very much. He says, I've been thinking about high altitude balloons in a desert recently. Thinner atmosphere without clouds may allow you to see way around the curve. Let me know. In a desert, thinner atmosphere without clouds. Yeah, I mean, if you had the prime, observation conditions would be great. I mean, the problem is when you gear up to do things like that, you usually are at the you're at the behest of wherever you're going on that particular day and whatever the conditions are. Ranty knows that. I mean, you can't really just pick the conditions. That'd be great if you could, but usually you just got to go out there and see what happens.
You just got to suck it up, and to be honest, I mean, the last 18 months, I would say, this bottom image has been my reality where I live. This has been, all I've been able to see is this bloody inferior mirage that gets in the way all the time. Now, we've already been through the inferior mirage and how the rest of this buildings and these sand dunes will be seen through it. So I've got so many videos out there about what lies behind the inferior mirage. That completely debunks that this is where the Earth curve is. It's just blockage. So it's just atmospheric blockage. Now, what's the cause of that atmospheric blockage? Is the Globers have now come on board with this. That okay, so this is no longer their reified edge of the sphere, but it is a blockage. It's an atmospheric blockage. But what's the cause of it? Well, there's people that say it's this mirrored water layer. Okay, which is a very good possibility. But if you want to go head-to-head with the Globers and you want to tackle them on this refraction issue, we can use the same refraction that they're using and just apply it on a plane.
Where would
tweak the mathematics a little, Right.
Where would the curve calcs put the curvature in this image here?
Pretty much where this fold line is.
Okay, that's what I figured.
And it always seems to be the case, is that, you know, this,
that's
this
your
fold
most
line,
often. That's your most often observation anyway.
Well, yeah, and that's why the globers were so adamant that that's where the reified edge of the sphere was.
Right, and I think that if you go back in the past, and you know, if we're talking about 1900s, 1850s, or something, you know, they wouldn't have had the equipment, or even, you know, they wouldn't even have known to go out and see over and over again to see that what we see on the top can actually happen at times, and they would have just drawn their curve maths from the bottom picture. Yeah, and you know, I mean, we've discussed this in length. The past year and a half or so for flat Earth on these optics side of things has changed dramatically. I mean, they've had to react to this. They've had to change the narrative because there's been overwhelming evidence that this inferior mirage is an atmospheric blockage and it's nothing to do with the leading edge of a sphere. Right. Then you've got the black swan photograph that completely just destroys them over the distance to the horizon, as well as, you know, other people doing tremendous work that they're on the back foot all the time now. They're always on the back foot, and I think this could be one of the final nails in the coffin. I don't like using the word refraction. I hate it. I hate using their mathematics on this. I really do. Well, sometimes you have to.
It sticks in my mouth to even talk about refraction because I've hated it so much for so long.
I can smell your bad breath from over here. No.
But seriously, I mean, you know, if you take their mathematics and you use it against them and you apply it on a homogeneous flat plane, then guess what? Things disappear from the bottom up.
Right.
And they agree with that, and there's no way around that for them. We don't need any looming, though. We don't need looming to happen, but they certainly do.
Because we can't find evidence of it.
And they can't prove it, though.
No. Well, I know, and I mean, they would say that this top picture is evidence of it. I mean, that's their evidence of it, because you're actually seeing beyond where the globe mass would put the horizon line. So that is their evidence of looming, but that's simply not, because you would actually see, like you said, you would see that the lineup with that, you know, say that home plate looking building there, whatever that building is straight ahead, you said, it always lines up in the same spot.
Yeah, it always does. It's never in a different position.
Right.
You know, never in a different position.
It doesn't rise up. It does. Sometimes it's not higher. Sometimes it's not, way above that post. I mean, in that case, then you would say, okay, well, something is looming here.
Well, you can even see it in this image here. I mean, you know, it's the top of this post, this yellow part, is just at the bottom of this nut there, and there's a little nut there, and it's just right next to it. Even with this inferior mirage, but it's high enough to avoid that. I don't know what would happen if it was the inferior mirage was super strong one day and it was way up here. Maybe that would manipulate that post down, but I've never seen it. I've never seen that post never being in the same position relative to the building behind it.
Yeah, well, I don't think that's necessarily what's happening. I think maybe you're right about the light's just not getting there, and if it doesn't get there, I think sometimes your eyes replace it. Could be with the reflection of the item.
Well, yeah, I mean, I just thought I would open this up for debate. You know, I would put it out there and say, okay, so from listening to these globers doing presentations on my show and discussing it with them in depth about this stuff, that I can turn their own science against them and say, okay, well, let's re-engineer these mathematics that are inside this curvature calculator. Let's apply this to a flat plane. Let's go with the idea that light bends through these gradients and navigates towards the denser region at the bottom. So all their science is saying this, but we just apply it on a flat plane and we get things to disappear from the bottom up. But like I say, we don't need looming, and they certainly do, and they can't prove it.
Thank goodness we don't need looming, because I can't find any.
Yeah, something else I wanted to say as well. It was like I did a little. Here we go. I'll do it with you actually, Jaron, if you don't mind.
Go ahead.
It's not going to take long. Do that for now. Right. Okay. So here we have. What I'm going to do now is I'm just going to draw like an ocean and a horizon. So here's the ocean. Right. Next, I'm going to draw the sky. So there's the sky behind it, a bit of a deeper blue. And next, I'm just going to put a building here right? And I'm going to put a building there, right? And I'm going to say to you, right, okay, so where's the horizon? There's the sky, there's the sea.
Right.
There's these buildings.
The buildings are in the sea?
The buildings are in the sea, yeah.
Okay.
We're going to say there are a couple of oil rigs that are in the sea.
Okay, so if the question is where's the horizon for this observer point, would be the line, I guess.
Yeah, well, pretty much. Just there, yeah?
The apparent position of it is correct, yes.
Yeah, so there's the horizon line, right? But then what I'm going to do is I'm going to play globe head with you, and I'm going to say, right, okay, well, that's too far. The horizon shouldn't be there,
right?
Because that isn't what the mathematics say.
Right.
Mathematics say that the horizon should be before these platforms here. So now where's your horizon? Oh well, the globe will say, oh yeah, well in that case then the horizon's there.
Right, and everything else is being loomed up.
And everything else is being loomed up. Yeah, exactly. And it's like they will deny their own eyeballs and their own senses and their own what they can see. I mean, I might be able to get that image up.
But they have to. I mean, this is the sad part about the whole thing is that they have to. They have no other choice. I mean, their globe mathematics, the curvature math, demands that a horizon line at the edge of the sphere be at a certain place. So if we're able to observe something different than that, then there has to be an explanation. For them, it's simply, even though you're right, they're just denying their own eyeballs right in front of you. Why? Because they've been taught that your eyeballs mean nothing, that your senses mean nothing, what you see means nothing. It all depends on what scientists have said and what math says. So yeah, and this, the black swan image. I mean, I guess these towers are being loomed up. They're lifted beyond the horizon, which should probably be about where the dark water ends.
Yeah, well, what it is, this is a wave that's just rolling in. It's just lapping up towards the shoreline, this darker area. It's just the other side of the wave that's heading towards you. It's It's only a couple of inches high, this wave, as it's just lapping up towards the shore. But the rest of it, I mean, but you're right. If this was if this was on a globe, essentially where this line is here, this little wave that's just lapping up, it's on a video, so it's very evident to see that this isn't the curvature of the Earth, this is a wave. But that would be where the horizon should be on their globe mathematics, because the horizon should be 1.33 miles away using their refraction stuff. And this platform here is, I think, 6.5 miles away. This platform here is 9.5 miles away. The horizon, which is clearly very, very evident in this, which is behind these platforms, is at least 20 miles away. At least 20 miles away. And then, so you ask a glober, you'll say, well, where's the horizon? And they will say, oh, the horizon is here. Until you say to them, well, that isn't what your Earth curve calculator says. Your Earth curve calculator says that the horizon should be before the platforms. Then I've had it on my show. Globers coming in and telling me that the horizon is down here.
Mm-hmm.
Yeah, no word of a lie.
And everything else behind it is being loomed up.
It's being loomed up.
The light is bending around the hump.
Bending around the hump, lifting everything up in perfect symmetry. Okay, yeah, there's a bit of an issue going on with a bit of Fermat's principle going on here for sure.
Sure.
Definitely things. There's a bit of distortion. Deviation from straight of these lights. But that's the boon, isn't it? That's the flare boon. So this was a working platform. This one wasn't. This was out of operation. But this flare boon, which was quite warm at the time, because it was operational, you've got a lot of heat going through this area, which is, why you're getting this major distortion on this particular part here. But the rest of it, it's pretty straight, a bit of wobbling going on, but they're hanging on to that belief that this wobble is like the refraction. Yeah.
It doesn't prove that it's being lifted up and all the water that it's in is somehow magically floating. And, there can be observation days where you go out there and you probably wouldn't see the water that's in front of those two platforms. And I've heard people describe that as looming, and we've shown every time when you see those boats supposedly floating out there, they're simply in the water, and you just can't see the water on that particular day. Skeptic936 just sent a super chat, says Ranty rocks. Can't disagree with that.
Thank you, Skeptic. But if this is their proof of looming, right? This is their proof of refraction and looming, right? And their proof of refraction and looming, wait for this, Jaren, is that everything's sort of like a little bit wobbly and squiggly, yeah? Right? That's what their claim is, right? That proves that it's being refracted, right?
Oh boy.
So so in that case then, what about my image? What about my image that isn't all wavy and bent out of shape? What about my image that's just a very clear image?
Refraction and looming.
Yeah, but why? How do I know that this isn't refraction now? Because it's just a very good image.
Right.
Yeah, there's no warping and twisting and bent metal going on here.
No.
So how are they now determining that this is looming? If their only claim for looming or proof of looming is because that those platforms are a little bit squiggly and wiggly. Yeah?
Yeah, well, I don't think they have any other answers. So it's kind of what I expect to hear from them.
Anyway, I think that's my presentation done. I think I was going to go and do something else, but I don't really need to. I think I've made my point. I don't want to ram it home too much.
Okay, whoa. It's been 2 hours? Can't be right. Maybe it
Has
is.
it?
I don't know. That's what my live thing says down here, but it might have been when I started the first show. That's crazy, though. Yeah, I guess it has been 2 hours now. I look at it. It's past. Yeah. Wow. Okay. That was longer than it was supposed to be, but we can be good there. So I guess go ahead and summarize your points if you were able to get across what you're trying to say in a paragraph. How would you describe it? Well, it could be two.
In a paragraph or two, right? Okay, so if you replace their 7.6R refraction and their globe presupposition and replace their scientific proof of light bending through the density gradients and apply that on a homogeneous flat plane with equal density layers, you will have bottom-up obstruction when trying to view distant objects, buildings across vast distances.
Sounds good to me. All right, well, awesome. Thanks, Ranty. I really appreciate you joining me and giving us all a great presentation to think about, and that's what I want. That's what I think people want. Something to think about, something to observe. You're doing a great job by going out and observing these things. Some people just simply can't get out there, don't have time, don't have the energy, don't have the desire. I don't know. They have their own reasons, but it's nice when there's somebody out there doing these things, putting these presentations together, and giving us kind of a condensed version of it and allowing us to come to our own conclusions. So I really do appreciate that. Anything you want to say to everybody before we head out?
Yeah, if you get the chance, guys, head on over to my channel, Ranty Flat Earth. I have a channel over there where globe earthers and flat earthers are welcome to do any kind of presentation, get into a debate with each other over a subject. If you have a speciality in something, or you think that you have more knowledge in one particular subject but don't want to actually put your own stuff on your own channel right now, come on over and do a presentation on mine, or get into a debate with somebody else that knows something very similar to you. And hopefully through this exchange of knowledge between each other, we might be able to break down what's lies and what's truth. Obviously everything's intermingled, and it's just a case of working together to find out what's going on. I feel that my platform allows that. It allows this open discussion to take place. And as I say, I'm unbiased if I moderate. I'm unbiased if I listen to your presentation. And yeah, it's a nice place over there. I generally get up to about 160, 170 people watching, so it's all very good. And I would like to get over 5,000 subscribers very soon, if that's possible.
All right, awesome. Well, I just showed people, and of course the description has his link, so head over there. He's got, 4,800 subscribers, so I think maybe we can get you 200 extra. Let's go ahead and give everybody a minute. If you're not subscribed to Ranty, you can just scroll down to the description of this video and head over there. Click subscribe, get him some love. And again, we appreciate the observations as always. And then, like Ranty said, you can find him on his channel doing his nightly show. And I agree with you about unbiased kind of, review of these presentations. I like it. I mean, if you sit there and just argue what you think all the time and say, well, I think you're wrong because this is what I think, this is what I think, I'm not sure we get as far as when we just listen, kind of open our minds to other people's opinions, ideas, and don't be so quick to judge because, I don't know, I just look at my history, look at everything that we thought at one time. When we first heard Flat Earth, we thought it was the stupidest thing ever, right? When we first heard a lot of things, we thought it was dumb. Why? Because that's your initial, that's how you've been built. That's how your mind works. That's how you will block anything that's new. You will say it's not true. You will try and defend what you already believe. That should be expected at this point. And it's something I've learned over the last 5 years really well, that whenever anybody says anything new to me, my first response is always going to be one of apprehension, one of kind of, wait, hold on, what now? I don't agree with that. But if I listen and kind of take it in, hear them out, and then look at things again, look at things with new eyes, with a new mindset, that's how your mind changes, and that's really how you can grow in your knowledge. So thank you everybody for the super chats. I really appreciate that. Again, definitely follow Ranty. Also sign up for his Patreon. If you want to sign up for mine, it's patreon.com/jeranism. You can also send me a tip at Venmo if you want. That's for just those in the U.S. Venmo at jeranism. And then also, you've got my address. I've given it out many times before, but if you want to mail me something, a book, a shirt, hey, anything. I'll take anything. P.O. Box 3044, Merced, California, 95344. Anything final before we head out, Ranty?
Yeah, anything final? Yeah, I'm just saying that I'm not putting my stamp of approval on this. I'm just putting this information out there for people to consider, and let's just say to the Globers, okay, well, we can use your own stuff against you, because we still don't know how light works and behaves. We, still haven't got to the crux of that. But there is plenty of information out there that suggests that this might be a possibility, but there's also probably other conditions that could give this same effect too. So there's nothing definitive, but it is just it's something in your arsenal. If a Globus turns around and mentions refraction, that you can then turn around to them and say, well, do you know what? We can do it on a flat plane. You can't prove it on your globe.
Right.
Oh, and Dr. John D's sending me over some lasers, 4 lasers, that can go about 12 miles, but I only need it for about 6 because I'm going to be doing a step ladder sort of like experiment where I'm going to put these lasers at incremental heights, all firing the same time across the bay at Blackpool, looking over towards Southport. So about a 6-mile distance, I'm going to have somebody looking from the side on, somebody looking from behind, and obviously myself from behind too.
Nice.
Hopefully that's going to happen in the next 2 weeks. So if anybody wants to help out, I will put something on my community tab about that. But the step ladder idea is that we'll see all these lights heading at the same time, and they'll be going through different gradients, obviously.
Interesting. That'll be awesome to see. And you said that'll be happening within the next few weeks?
Yeah, hopefully within the next 2 weeks.
Awesome.
Yeah, Dr. John D's sending them up to me.
All right, great. That'll be awesome. Looking forward to that. All right, well, thanks, Ranty, one more time. Appreciate it. You're welcome back anytime you want to do a presentation. I think people like them, and even if they don't, I like them, and people don't have to watch. They don't want to watch a Ranty presentation. When you see a video come out and it says something, something, something with Ranty Flat Earth, don't watch it. Guess what? I'll be fine. Ranty will be fine. We'll be just glorious. Don't worry. So, yeah, that's the Ranty presentation. Really appreciate you guys watching. We have the lounge tomorrow. Same time, 12 noon, so tune in for that. I think UAP will be joining us and the regular crew. I'm not sure about Yuru or who's going to be there, but it's always just a open platform. People can come and just hang out, and we just have a little chat. And then, of course, we have Globusters coming back on the 9th, so that'll be good to get the guys back together for Globusters. And that's about it. So I think, am I missing anything? Do we have something going on Saturday? No, I can't remember. And then, of course, we have Raw on Monday. So lots coming up if you need something to watch, or you can just tune into Ranty's channel, like he said. And there's always something going on there every day. There's tons of Flat Earth content all over the place. You can never get enough. So appreciate you guys watching. Thank you so much. I remind you to do your own research, because when you do, you'll never again believe what you've been taught. This has been Jeranism with Ranty. Till next time, guys. Peace.
Peace.